We are continuing our videos on notes for Unit 3. We are in section 3.7, where we will explore the graphs of the other trigonometric functions. We have seen the graphs of the sine, the cosine, and their transformations. And now we are missing the tangent, the cotangent, and in a following video, the secant and the cosecant. So to start with the graph of the tangent, I want to remind you that we discussed that the unit circle is a circle that has the center at the origin, a radius of 1, and it looks really tiny in the Cartesian coordinate system. And the reason that we end up enlarging it is that because we want to do a lot of work inside that 2x2 square, so we make it really large, and then the two axes are showing in the middle of the circle. So this is the enlarged unit circle. And I want you to consider the vertical line x equal to 1, which is right here. X equal to 1 is this vertical line. So in the graphing paper, it will look like this. This is x equal to 1. And this line is tangent to the circle at the point 1, 0. And assuming that I have a random rotation theta, this is the terminal side of theta. Let's say this is theta. We know that the point on the circle that is the intersection of the terminal side of theta and the circumference of the circle has coordinates x, y that correspond to the cosine and the sine of theta, because the radius of the unit circle is 1. So let's call this point of intersection, let's call it T. And let's give some other names. So let's call this A and B. I'm also going to draw the triangle that attaches to the x-axis. So let's call this C. The triangles, and let's call this point P. The triangle A, C, and P is a right triangle at C. And it is similar to the right triangle ABT. ABT has the right angle at B. And when we have similar triangles, their corresponding sides have equal ratios, which means the AC over CP, that are the two legs of the smaller right triangle, that ratio is equal to the ratio of the corresponding sides on the larger triangle, which will be AB over BT. And we know that AC is the x-coordinate of point P, and CP will be the y-coordinate. So this is x over y equals AB is the radius of the circle, and AB is equal to 1 over BT. So if I solve this equation for BT, BT will equal to y over x if I flip the two fractions on both sides. But y over x is the tangent of theta, because it is the sine over the cosine. So actually, when I am on a unit circle and I have a random rotation theta, a random angle theta, if I extend the terminal side, the coordinate on the vertical number line, the tangent number line, this is the tangent axis, that length, assuming that this is the 0 of that axis, that length will equal to the tangent of theta. So this number, which is a coordinate on that number line, is equal to the tangent of theta. Now we have to understand how that axis looks like. And it looks exactly like the y-axis, so they are identical to each other. It has a 0 here. Let me zoom in a little bit, maybe we can see a little better. So it has a 0 here, then it has a 1, then it has a 2, then it has a 3, then it has a 4, then it has a 5, and then going down it has a -1 and a -2 and a -3 and a -4. So when we are enlarging this is the one on the vertical axis, which is the sine axis, and this will be the one on the tangent axis. Maybe that's a 2 on the vertical axis, that will be the 2 on the tangent axis. And the tangent axis just goes up. This is -1 on the sine axis, this is -1 on the tangent axis. This is -2 on the sine axis. If that thing was going down, this will be -2 on the tangent axis, etc., etc. And every time I'm looking for the tangent of a particular rotation, I will be extending the terminal side. So I want to graph the tangent. The y-axis will be the tangent of theta, and the x-axis will be the rotation. And we will always start with 0 rotation here. The positive direction is this way. And that will be 0 rotation right there. And the positive direction will be this way. So when I am at 0 degrees and I take the terminal side of 0 degrees, that terminal side cuts the tangent axis at 0. Therefore, the tangent of 0 is 0, and this point 0, 0 is a point on my graph. When I have exactly 45 degrees, then I am on the diagonal of this square. And the diagonal of this square hits the tangent axis at the number 1. And the tangent of 45 degrees is equal to 1. So I have a point pi/4 with 1 as part of my graph. It's right here. And then as I increase the rotation theta, approaching the 90 degrees, what happens is that this tangent increases. So I will have tangents that are becoming very, very large. And when I am at 90 degrees, the terminal side will actually never intersect the tangent axis. So when I have the angle pi/2, I have an asymptote there for the tangent. And right before pi/2, so as theta was approaching pi/2 from the left side, my tangent of theta was approaching some very large numbers, positive numbers, so infinity. So the graph of the tangent actually has an asymptote here at x equal to pi/2. As soon as I pass quadrant 1, so I have now passed the 90 degrees, I continue in the positive direction. I continue my rotations. I cannot intersect the tangent axis when I extend this terminal side. So to fix that problem, what we do is we extend the terminal side in the backwards direction. And in the backwards direction, I will be hitting the tangent line in negative values. And the closest I am to 90, the farther away I will be towards the bottom of the tangent axis. And as I move in quadrant 2, the tangent will be negative, but will be coming closer to 0 until I am at 180 degrees and my tangent will be exactly equal to 0. So what happens here is that after pi over 2, I come asymptotic from the negative infinity. And when I am here exactly at 135 degrees, I will have a reference angle of 45 degrees, and that will hit exactly at the other corner. So I will have a -1. For at 3 pi quarters, I will have a -1 for my tangent. And then at pi, I will have a 0 for my tangent. So it's going to go like that. And then as soon as I pass pi and I am now in quadrant 3, I will start having positive tangents. Positive tangents at exactly 225 degrees, I will have a reference angle of 1. So at 5 pi quarters, I will have a 1 for my tangent. And then as I approach 270 degrees, my tangent will be increasing until at 270 degrees, I will not be able to intersect with the tangent axis. So at 3 pi over 2, I will have an asymptote. Now pay attention that when I was in quadrant 3, I was extending backwards in quadrant 1. So I was actually repeating in quadrant 3 the evaluation of tangent that I had in quadrant 1. So the repetition comes every pi. When I'm in quadrant 3, 180 degrees away from quadrant 1, I'm repeating myself. So after I pass 270 degrees and I'm in quadrant 4, I will be able to actually intersect with my tangent axis towards -infinity. I will keep going in that direction, increasing but being negative until I hit 360 degrees. So at 2 pi, I will be at 0, and then I will just repeat the whole process again. Now, if I was rotating in a negative direction, so let me try to clean up a little bit here so we can see what a negative rotation would look like. All right, so if I was in the negative direction, so I'm gonna go in this direction now, rotation. Rotation in the negative direction will be going towards quadrant 4. My terminal side would be hitting the tangent axis in negative tangents. When I am exactly at negative pi quarters, I would be hitting at -1 because I will be the diagonal of this little square over here. So I have a point negative pi over 4 with -1, which is here. And then as I approach -90 degrees, I will have a very large in absolute value negative tangents until I don't intersect anymore. So at negative pi over 2, there will be an asymptote here. And my graph will go towards -infinity, asymptotic to that asymptote. But as soon as I pass -90 degrees and I'm now in quadrant 3, I will have to extend the backwards direction of my terminal side to hit the tangent axis in some really large positive numbers. So on the left side of negative pi over 2, I will be coming from really high tangent values. When I hit -135 degrees, my reference angle will be exactly at 45 degrees. And at 45 degrees, I will hit that 1. So here at -3 pi quarters, I will have a 1 And then at pi, negative pi, I will have a 0 for my tangent. And then after that, I will just keep repeating. I will have another asymptote at negative 3 pi over 2. I will have another intercept at negative 2 pi, and another asymptote at negative 5 pi over 2, etc., etc., etc. This is what the branch of that's what the graph of the tangent looks like. And the graph of the tangent repeats every pi. Every 180 degrees, I get this wave. Because every 180 degrees, I start trying to approach the tangent axis with the opposite side of the terminal side than the one I had the 180 degrees before. So if you pay attention here, the domain of this graph is all real numbers except for the values of x that I have asymptotes at. And these are pi over 2, 3 pi over 2, 5 pi over 2, negative pi over 2, negative 3 pi over 2, which are odd multiples of pi over 2. The range is all real numbers because these branches go from all the way to the bottom to all the way to the top, and those terminal sides intersect the tangent axis from negative infinity to positive infinity. The period is only pi. The asymptotes are vertical lines at odd multiples of pi over 2. We have 3 key points. 0 with 0 is an intercept, and then 45 degrees has a tangent equal to 1, and negative 45 degrees has a tangent equal to negative 1. However, there are 5 critical x values, the beginning and the end where we have asymptotes, and then the quarters in the middle where we have the specific points that we graph. So the key values are negative pi over 2, that's an asymptote, negative pi over 4, that's a point, 0, that's an intercept, pi over 4 is a point, and pi over 2 is an asymptote. The graph of the cotangent is a similar situation. The cotangent axis is actually the horizontal line y equal to 1. And I can do a similar proof to demonstrate to you that the terminal side of any rotation will intersect the cotangent axis in a real value, in a coordinate that is equal to the cotangent if measured from the 0 of the cotangent axis, which is here. So the 0 of the cotangent axis is here, the 1 is there, the 2 is here, the axis goes to the right towards positive infinity. This will be negative 1 here, negative 2 here, and the axis will go to the negative infinity towards the left. On the vertical axis, I will be measuring y equals the cotangent of theta of x, x being the rotation. I will start the rotation at the 0 of the axis of the circle, going positive counterclockwise and negative clockwise. And for every one of those rotations, I will be measuring the point of intersection between the terminal side of my rotation and the cotangent axis, and then its distance from the 0 of the cotangent axis. Now, when I am at 0 degrees, the terminal side of 0 degrees actually does not intersect the cotangent axis, and therefore I have an asymptote there. The cotangent of the 0 degrees is undefined. So this is an asymptote at x equal to 0. that I cannot cross. And then as soon as I pass, I start moving over from 0, going in the positive direction. This terminal side will go and intersect the cotangent axis in some very large positive number. So on the right of 0, as I start having positive rotations, I'm coming down from the asymptote with a positive cotangent at very large values. And then when I hit 45 degrees, I'm gonna be at the diagonal of this square, the 1 by 1 square created in the fourth quadrant. So I will have a point, pi quarters with 1. So this graph will have to go through that point. And then as I approach 90 degrees, my cotangent becomes 0. So I have a point at pi halves with 0 cotangent. And then after I pass pi halves in my rotation, my cotangent becomes negative. And when I hit 135 degrees, I'm at the diagonal of the square in the 1 by 1 square in quadrant 2. So I will have a 3 pi quarters with a negative 1 for the cotangent. And then as I approach 180 degrees, I will get very large in absolute value, but negative cotangents. When I am exactly at 180 degrees, this terminal side will not intersect the cotangent axis. So I will have another asymptote at x equal to pi. And let me see if I can move this a little bit this way. There we go. And my equation, oops. And my equation. Okay. So that's at x equal to pi. All right. After I pass quadrant 2 in my rotation, and I'm now continuing in the positive direction after pi, I will not be able to intersect with the cotangent axis and my terminal side. Therefore, I'm going to start going backwards or trying to intersect in the opposite direction. That makes me repeat quadrant 1. So the opposite direction of my terminal side is exactly the direction of my rotation, the terminal side of my rotation in quadrant 1. So this branch from 0 to 90 degrees will now repeat from 180 to 270 because I will be trying to intersect in the backwards direction from my initial side, from my terminal side of the rotation. So I will get to the cotangent of equal to 1 when I'm here at 225, because then I will have a reference angle at 45 degrees in quadrant 1. I will, when my rotation is 270 degrees, I will hit 0 for my cotangent. So at 3 pi over 2, I will have 0 for my cotangent. After that, I will be hitting in the negative direction. So I will be repeating whatever I was doing in quadrant 2. When I hit 315 degrees, I will be back at a cotangent of negative 1, etc., etc. When I hit 2 pi, I will be where I was when I started, rotation 0. So at x equal to 2 pi, I will have another asymptote. And that thing will keep repeating. Now, if I start and I do negative rotations, so let's go red with negative rotations, then I will be going in this direction. I have an asymptote when x was 0, but as soon as I hit some negative rotation, I can extend in the backwards direction. I will end up with a negative cotangent. As I continue to approach towards negative 90, my cotangent will be increasing, decreasing in absolute value, but increasing as a negative value until at negative 90, I hit 0 for a cotangent. So it will be going like this. Of course, so that will be negative pi over 2. Of course, when I was at negative 45, I would be hitting the diagonal of the 1 by 1 square in quadrant 2. And that means that I will have a point of negative pi over 4 with negative 1. And then as soon as I pass over negative 90, and I am now here in quadrant 3, the opposite direction of my terminal side will be in quadrant 1. So I'm going to be repeating the tangent values of quadrant 1. I will end up with an asymptote at x equal to negative pi. After that, I will be repeating myself. I will have an intercept at negative 3 pi over 2. I will have an asymptote at negative 2 pi, and so on. So this is the graph of the cotangent. The domain is all real numbers except for where the asymptotes occur. And the asymptotes occur at multiples of pi. The range is all real numbers. The period is pi. So these branches repeat every 180 degrees. The asymptotes are at multiples of pi. The three key points are pi quarters with 1 for the cotangent, pi halves with 0, that's an intercept, and 3 pi quarters with negative 1. But the 5 key values include the asymptotes. So we have 0, pi quarters, pi halves, 3 pi quarters, and pi. And they occur at quarters of the period of this function.